Good morning students. Today we'll be discussing the topic on operations of graph under the model 5 introduction to graph theory. So in this operations of graph, basically we'll be having union, intersection and ring sum. So basically union is nothing but, you already know the concepts of union in these sets. So for example, if A is a set with 1, 2, 3 and B is a set with 3, 4, 2, 3, 4, then A union B is nothing but 1, 2, 3, 4. Similarly, the concept is in the graph. In the graph, we have two graphs, G1 and G2. So the G1 union G2 is nothing but union of their vertices of both the graph, that is capital V union V2, and comma union of the edges, E1 union E2. That means edges of first graph union edges of second graph. So if these two are the graphs, the vertices which are common, for example here we have V1, V2, V4, V5, V3. Here V5 is the extra vertex, here V6 is the extra. Rest vertices are common in the both. So whatever the graph edges are there. Now for example, same graph I'll be drawing here, but V3 is over here. Why? That because V3 is again connected to V6. So that's why I've drawn here. So if you see this graph, this section is drawn completely same graph, but from V1 there is an edge to V3. V1 there is an edge to V3, and from V2 there is an edge to V3. And from V1 again you have V4. In this graph you have an edge V1 to V3 and V2 to V3. I mean V1 to V3 there is an edge. So combination of both the graphs I am going to draw in this particular graph, that is G1 union G2. Similarly, G1 intersection G2 would give me nothing but V1 intersection V2, E1 intersection E2. Now if you see in this set, A intersection B would give me just 2, 3. Similarly, both the graphs you will be comparing over here, both the graphs. So which is the common vertices? If you see, it is V1, V2, V4 and V3. V1, V2, V3 and V4. So that points I am going to draw, and whatever the vertices common I am going to V1, V2, V3, and whatever the common edges. So you have V1 to V2 here also you have, and V1 to V4 you have, even here you have V1 to V4. So I have drawn this graph, and V2 to V4 you check, V2 to V4 is there, V2 to V4 is there. So it's drawn V4 to V3, V4 to V3, and V3 to V2, V3 to V2. So these all edges are, both edges are common in both the sides. So I'm going to draw the G1 intersection G2. So this is the concept of union. This is the union graph and this is the intersection graph. Similarly the ring sum of the graph of G1 and G2, if you want to find the ring sum of these two graphs G1 and G2, it is actually represented as G1 ring sum. This is the sum, that is delta symbol, that is equal to V1 union V2, E1 delta symbol E2. Now whatever both the vertices are there, that union, all the vertices should be there. The formula for the ring sum is of G1 graph G2 is V1 union V2. That means all that 6 vertices, V1 to V6 vertices are there, right? That vertices will be there. That is V1 to V6 will be there. Whereas E1 in E1 ring sum E2 is nothing but, this symbol is nothing but the symmetric difference. This symbol is actually used for the symmetric difference. And here this symbol is in shape of ring, so it is called as ring sum. So G1 ring sum G2 will give you V1 union V2, E1 ring sum E2. So this is nothing but E1 ring sum E2 is nothing but, it is a symmetric difference between E1 union E2 minus E1 intersection E2. Minus E1 intersection E2. That means what? A combination of this is E1 union E2. If you see edges, we have combined and drawn this particular edge. This edge minus intersection of these edges, whatever the edges is there. Vertices will be there, but E1 intersection E2. If you see the E1 intersection E2, these are the edges. So you have to separate from this graph V1 to V2. This edge is subtracted, and V1 to V4. This edge is subtracted, and V2 to V4. This edge is subtracted, and V2 to V3. This edge has been subtracted, and then you have how many edges? 1, 2, 3, 4, and V4 to V3. this edge has been subtracted. So subtracting that edge, the graph would be like v1 to v5, v1 to v5, and then you have v1 to v4, and then you have v4 to v3. From there you have one edge to v6, and then again v6 to v2, and then again v1 to v3 pending is that graph. Similar, this same graph is being drawn over here. So this is regarding the ring sum. Now when you have two graphs, the ring sum between those two graphs is nothing but union of the vertices. All the vertices you are just pointing out, that is v1 to v6, comma ring sum between the edges, that is e1 ring sum e2. E1 ring sum e2 is nothing but E1 union U2. Edges of this minus edges of this would give you this particular graph. So this is regarding the concept of union, intersection and the ring sum. Next is regarding the decomposition. We say that the graph G is decomposed or partitioned into two subgraphs, G1 and G2. In case if G1 and union G2 would give you G, and G1 intersection G2 will give you null graph. So this is regarding the decomposition of the graph, or you're going to partition the graph into two subgraphs. For example, you know, if you have seen this G1 union G2, it would give you the main graph, okay? It would give you the main graph, and when you do the intersection, we say that it is a decomposition in case if you get a intersection is equal to null graph. So this is just a definition of the decomposition. Next we have the concept of deletion. Here we'll be seeing the concept of edge deletion subgraph as well as vertex deletion subgraph. So first let me go to the example, then I'll see the definition. So this is regarding the main graph, what is being given, and this is regarding the vertex deleted graph. If you see this vertex deleted graph, subgraph, and edge deleted subgraph. So this is vertex deleted subgraph and this is edge deleted subgraph. Now you know that this is a major graph, I told major graph, which has a one vertex called V and one edge, just I have named it as H. Now from this graph, if I subtract the vertex, then I get vertex deleted graph. Now what is the meaning of this? When I subtract the vertex over here, I am going to delete that particular edges connected to the incident to that particular vertex also. So when I delete those vertex that is being incident on that edges, I mean those edges which is incident on those vertex, I am going to delete. Now for example, V I deleted, G minus small v, then I would have only A, B, C, D, and these three edges will not be there which was connected to the V. That is regarding the vertex deleted subgraph. So this is an example for the vertex deleted subgraph. Similarly, edge. Now for example, I just want to remove this an edge of this G minus E, then this edge will be deleted. So this is an example for what edge is being deleted, but it will not delete any vertex from that particular graph. It will not delete any vertex from that particular graph. So if you see over here, if V is a vertex in a graph G, then G minus V denotes the subgraph of G obtained by deleting. If V is a vertex in a graph G, then G minus V denotes the subgraph of G obtained by deleting V and all the edges incident on V. So same definition I told. From the main graph, if you delete one particular vertex, whatever the edges is there connected to that incident to that particular vertex, that edges will be deleted. This graph is represented as G minus V, G minus V, and the graph is called as vertex deleted subgraph of G. It should be noted that the deletion of vertex always includes deletion of all edges incident on that particular vertex, as I told in the figure. And edge deletion is nothing but if E is an edge in the graph, then G minus E denotes that subgraph of G obtained by deleting E from G. Then this subgraph G minus E is referred to as an edge deleted subgraph of G. So this is an example for graph, and this is an example for vertex deleted subgraph, and this is an example for the edge deleted subgraph. Next we have complement of a subgraph. Now what is the concept of complement of a subgraph is we have a main graph and then we have a subgraph. So here given a graph G and a subgraph G1 of G, suppose in this is the main graph, okay, and whatever the darkened lines is there, that means this darkened line is there, that is actually taken as a subgraph. So they told that entire graph is taken as the main graph, that is G, and this graph is taken as the subgraph. Given a graph G and a subgraph G1 of G, this is the subgraph and this is the graph. The subgraph of G obtained by deleting from G, that means by deleting this subgraph, that means this and this and this, you'll get a graph, right? You'll get a graph. If you just delete this and this and this, you'll just get this shape, you'll get it. So deleting the subgraph of G obtained by deleting G from all the edges that belong to G1 is called the complement of G1 in G, and it is denoted by G minus G1. Okay, so this is the main graph, this is the G1. If you subtract this graph from this, then you will get the complement of the subgraph. So this is regarding the definition of the complement of the subgraph. Next we have the concept of complement of the simple graph. Here we have noted that every simple graph of order n is a subgraph of the complete graph Kn. If you remember the concept of simple graph, Kn, that is nothing but which will tell you the number of vertices or order. Now here K4, how many vertices are there? 4. So we have noted that every simple graph of order 4 is a subgraph of the complete graph K4. If G is a simple graph of order n, now this is a simple graph of order 4, then the complement of G in Kn is called the complement of G. It is denoted by G bar. Now for example, if this is the simple graph, okay, K4, and from this simple graph, if I've drawn this G, if G is a simple graph of order n, that means if this is a graph and this is the K4, we tell the complete graph, and this is a simple graph if I tell, okay. What I've done is I've taken this simple graph, and if I subtract this graph from this, then I would get the complement of the simple graph. Okay, so that is the meaning. So that every simple graph of order n is a subgraph of the complete graph Kn. So this is the simple graph and this is the complete graph. Okay, so this definition is very important. This is represented as K4. So a simple graph of order n is a subgraph of the complete graph. So this is the subgraph of this complete graph. If G is the simple graph of order n, then the complement of G in Kn, complement of G in Kn is called complement of G of, that is nothing but complement of simple graph, and it is denoted by G bar. So subtracting this from this graph would give you this. Thus the complement of G of simple graph with n vertices is the graph which is obtained by deleting those edges in Kn which belongs to G. The meaning is same what we have seen in this particular concept itself, but thing is, complete graphs, from the complete graph I'm going to draw the simple graph. So this simple graph, if I delete from this complete graph, would give me the complement of the simple graph. So this formula is very important, that is G bar is equal to complete graph minus normal graph. Okay, that is also represented as ring sum, difference between the complete graph and the normal graph. So this is regarding the complement of the simple graph. Example 1 is regarding show that the complement of a bipartite graph need not be a bipartite graph. Now what we are supposed to do is, if we consider a bipartite graph, the complement of the bipartite graph should not be a bipartite graph. So you should give an example considering the bipartite graph. So let us take an example for the bipartite graph which is of order 5. So the figure below is considered to be a bipartite graph, of order 5. Let us take it as order 5. Now if the figure example is V1, okay, V1 and V2 and V3. If you remember the definition of bipartite graph, then there should be a two vertices set and there should be a disjoint set. Okay, so that would be V4 and V5. Now this we are taking one set and this we are taking as one set. So let us draw those two vertices. And one more thing is, there should not be an edge between these vertices and edge between these vertices, but there can be an edge from this to this set of vertices. So let us draw such a way that V1 to V5, and it also goes to V2 from this to this, and then again it goes from V3 to V4, and from V4 let us take it to V2, and then let us take to V3. Okay, so this I have considered to be a bipartite graph. So this is I have considered to be a bipartite graph. So figure below is considered to be a bipartite graph. Now the complement of this graph would be, this is a A. What would be the complement of this particular graph? We should show that the complement of this particular graph is not a bipartite graph. Now whatever the edges is pending, that would be a complement graph. So just draw those set of vertices, that is V1, V2 and V3, and then again V4, and then again V5. So over here just draw this particular complement. V4 to V5 there was no edge over here, so we are supposed to draw over here. V4 to V1 we are supposed to draw, V1 to V2, again V2 to V3, and again this graph, and then again V1 to V3 there is a pending, I mean there is a path. This path we are supposed to draw, this path, this and entire path. So I have drawn this entire path graph. Now when you compare over here, check whether it is a bipartite graph. No. Why it cannot be a bipartite graph? Because you cannot have a edge within the same set of vertices, V1 to V2, V2 to V3 and V1 to V3, and here also this edge, if it should be a bipartite graph, there should not be an edge between these two vertices, between these and this edge also. So it is not a bipartite graph. So the figure, the complement, so therefore the complement of this graph shown in figure B is not a bipartite graph, So this is example 1. Let us go to the example 2. Let G be a simple graph of order n. If the size of G is 56 and the size of complement is 80, what is n? You need to find the value of n. Okay, so if you just go to the concept of simple graph, if you just go to this concept what I've taught regarding the simple graph, we considered a complete graph K4, it had certain order, and from that I drawed a subgraph which is a simple graph, and the complement of that would give me this particular graph. So we had already added a formula, that is G bar is equal to complete graph minus subgraph. So if you just remember, the complement G bar of a simple graph G with n vertices is the graph which is obtained by deleting those edges in Kn. Okay, now Kn is nothing but it is regarding the complete graph. So this concept we are going to use in the example 2. So by the definition we know that G bar is equal to complete graph minus the subgraph what we have considered as G. Therefore, so let G be a simple graph of order n. So this is a simple graph of order n. The size of G, that means size of G means size is nothing but the number of edges. The number of edges is 56 of this, and number of edges of a complement of graph is 80. Then what is n you have to find? What is n? Now you know that this would be, we'll write this in terms of size of G bar is equal to size of Kn minus size of G. Now just recall by the concept of the graph theory, the Kn, that is the number of edges in the complete graph, is nothing but, if you just remember the formula, the number of edges in the complete graph is nothing but half into n minus 1. We have already solved this problem in the previous sessions, so just recall this formula and I'm just going to use it over here. Since size of Kn is nothing but half into n minus 1, then size of G bar as it is I'm going to write minus size of G. Okay, so we know size of G bar is nothing but 80, and half into n minus 1 is size of Kn, and minus size of G is 56. So just 80 plus 56 is equal to half into n minus 1. So it would be nothing but, again if I take half into this, 80 plus 56 would give me 136. So I'll just write over here 136, 90, 100, 136 into 2 is equal to n into n minus 1. So that is nothing but, we'll get it in terms of 272 is equal to n into n minus 1. So find the term which is a multiplication of in terms of n into n minus 1. So if we just try with 17 into 16, we'll get 272. So you can put n as 17 and 17 minus 1 would give you 272. So therefore n is equal to 17. N is equal to 17. So this is the order of G. So I'll repeat again, let G be a simple graph of order n he has given, and G bar is the complement, and it is you're obtaining from the complete graph. So you know the formula that complement I'm going to obtain from, you just see here, complement of I'm going to obtain of this simple graph, complement of this simple graph I'm going to obtain is nothing but this minus this graph minus this would give me the complement. So you can see kn minus g would give the complement. Same formula I'm going to apply over here and I'm going to solve. And this one more formula we had already seen in the last sessions. So half into n minus 1 is the size of the complete graphs. I'm just using those formulas and I'm trying to find the value of n. So this is regarding the example 3. Next is example 2. Next is regarding the example 3. If a simple graph G of order n is isomorphic to its complement G bar, show that n or n minus must be a multiple of 4. So over here, I'll just take an example of 2, the graph and the complement. I'll just show you for the consideration. So let this be a simple graph, okay, with A, B, C and D. Now what would be the complement? Remaining edges would be the complement. So just draw over here A, B. This is graph G. So A to B, A to D, B to C. I'm supposed to draw, that is A to D and B to C. This is G bar. This is the complement. If A is a simple graph G of order n, so you can see order is 3. N is isomorphic to its complement G bar. 1, 2, 3. Check for isomorphic. Both the graphs are isomorphic. Okay. You just try to check for isomorphic. These both graphs are isomorphic. Then they are told that show that n or n minus 1 must be a multiple of 4. Now, since G is equivalent to G bar, G is equivalent to G bar, that is based on the both have the same number of edges, since they told that these both graphs are equal, since G bar is equivalent to G, both G and G have the same number of edges. Also the total number of edges in G and G bar, also the total number of edges in G and G bar taken together must be equal to, if you remember the concept, number of edges G and G bar taken together must be equal to Kn. If you remember, must be equal to the number of edges in Kn. So if you remember, this is the simple graph, and if it is a complete graph, it would be like A to B, B to D, C and D, A to C, A to B, B to D, C to D. So again this would be the edge would be this. So this would be the complete graph. If you just recall the concept, here we have shown a simple graph. I just considered this. So if I subtract, this is a complete graph. If I subtract this from this, I would get this. Okay, I would get this. So if you just remember the concept of a simple graph over here, same concept I've used in this particular example also. So if you subtract this from this, you will get the complement. So what is this statement he is told? Also the total number of edges in G and G bar. Here we have 3, here we have 3. So here we have 3 edges, here we have 3 edges, here we have totally 1, 2, 3, 4, 5, 6 edges. So the total number of edges in G and G bar taken together must be equal to the number of edges in the complete graph, Kn. So you can see over here, since Kn has, we know that since Kn has n into n minus 1 divided by 2 edges, it follows that it follows that it has Kn has 6 edges, right? So here it is what, again divided by 2, 6 divided by 2, so it should be n into n minus divided by 4 edges. So it follows that each of G and G has n into n minus 1 divided by normal this 2 into 2. Why? n into n minus 1 by 2 would give you what? N into n minus 1, 2 would give you 6. Divided by again 2 would give you 3 of this and 3 of this. So it has n into n minus divided by 2 into 2 edges. Thus n into n minus 1 divided by 4 must be a positive integer. Therefore n or n minus 1, if you see, it should be divisible by 4, right? N or n must be a multiple of 4, because you should not get a decimal, because if it is a decimal then it is a half edge, multiple of 4. So this is regarding the example 3. So what they have told is, if a simple graph of order n is isomorphic to its complement, yes, these both graphs are isomorphic, show that n or n minus 1 must be a multiple of 4. So I told both they have same number of edges. Also the total number of edges is equal to kn. Since kn is this, half of that would give you what? The simple graph and the complement graph. So half of that would give you n into n minus 1 divided by 4. So since they have told that, show that n or n minus 1 must be a multiple of 4. So n into n minus 1 must be a multiple of 4. So this is regarding the example 3.